Remembers from yesterday what resonant frequency means? Yep, good. The natural frequency at which something wants to vibrate. So everything has a natural frequency, right? Everything has a resonant frequency at which it wants to vibrate. Yesterday I showed you my keys swinging back and forth. They have a natural frequency at which they want to vibrate. Okay, the period of those keys swinging back and forth is 2 pi square root L over G. The resonant frequency of those keys swinging back and forth is 1 over 2 pi square root L over G, right? 1 over the period. The natural frequency of the resonant frequency of the keys swinging back and forth, or of any pendulum swinging back and forth, is pretty easy to find. The resonant frequency of lots of other things is much harder to find, but everything still has that natural frequency at which it wants to vibrate. What happens if I apply a force, or if something applies a force at the natural frequency? So we're not saying that you have to apply a force harder to meet the natural frequency or whatever. Okay, we're not suggesting anything about how hard you have to push the force, just the rate at which the force is applied. If we match the rate of the natural frequency with the rate at which we apply our force, what happens? The disturbance grows. That's a phenomenon called the resonance. When you match the natural frequency with a force, okay, the disturbance grows, and that's called resonance. Give me an example of when resonance might occur. Besides the swing set, right? That's one that I gave you yesterday, right? It's swinging back and forth like this. You push it at a random frequency, and it still swings back and forth at the same frequency, but the disturbance doesn't grow. But if you push it at the right time, now, now, now the disturbance grows and grows and grows, right? And that's what you do from the time you're 5 years old on a swing set, is push it at the right frequency so that you have resonance, even though you don't know what it's called when you're 5 years old. Okay, trampoline, yeah. If you jump up and down on that trampoline and you match the natural frequency, then you can go higher and higher and higher, right? If you don't match the natural frequency, then what happens? Yeah, exactly. That's exactly what happens, right? Anything else? I mean, there's a million examples of these, right? You can just think for a second. Think about one of them. Kelly? All right. The example that I gave you yesterday, driving my Conquer at 94 kilometers per hour, it was actually from 94 to 100. It vibrated at that frequency. There was a resonant frequency of something under the dash that would vibrate if we matched the natural frequency. In other words, if the engine turned over at the frequency of the resonant frequency of that thing that vibrated between 94 and 100 kilometers per hour. What about this? If you guys have all heard the story of the opera singer, right? The opera singer singing and breaking glass. Is that possible, by the way? Is it possible for an opera singer to break glass? It is actually possible. It would be very, very difficult to do it, but it is possible under certain circumstances for the opera singer to break glass. Well, how does she do it? Firstly, she has to sing fairly loud. Okay, we said that resonant frequency and resonance doesn't have anything to do with volume or with the intensity of the force, but it actually does somewhat. But that's not the most important thing. The most important thing is that the glass would have a resonant frequency, and the opera singer with her voice would have to match that resonant frequency. And you know that when you speak, you have a certain pitch or a certain frequency of your voice. Boys tend to have a lower pitched voice or a lower frequency than girls. Girls have a higher frequency than boys. Everybody has a unique frequency. An opera singer, if she can match the natural frequency of the glass with a really high pitch, then what happens? Well, the glass starts vibrating. Or she can match it with a high enough intensity that it can keep vibrating to the point of failure, of structural failure, and the glass can actually break. Although, like I say, it would be very difficult, A, to match the natural frequency of the glass, and B, it would be difficult to do it with enough intensity for enough time to actually break the glass. But yeah, theoretically possible, yes. What about this? You got this this river that you got to cross, this road on either side, and then we have this bridge that crosses this river. Does that bridge have a natural frequency? Yeah, it does. We talked about the pedestrian bridge in Okotoks yesterday. If you've ever walked across the main bridge crossing the river, right, the car bridge that crosses the river, you know that it kind of bounces up and down as well, right? It resonates as well. There's no danger to that. It's designed to do that. It's supposed to move a little bit so that it doesn't buckle and break. But if you could match the natural frequency of that bridge, then you could cause the vibration to grow and grow and grow. Sometimes what happens in a parade is you've got all kinds of things going on in a parade, right? From the horses hauling the horses, whatever, with the bands behind them, to the soldiers marching. And sometimes what they'll do when soldiers are marching across the bridge, they all march in stride, right? Sometimes when they march across the bridge, they'll break stride. Why do you think they might do that? Why do you think they might break stride when marching across a bridge? So why do you think they might not march in stride together? Just for the bridge. And then when they get to the other side, back in stride again. Well, what if you got 100 soldiers marching up and down on this bridge right here, marching in stride together? And what if they happen to be marching at the natural frequency of the bridge? Well, now you don't just have one guy or one girl applying a force on the bridge at the natural frequency. Now you got 100 or 200 or whatever the case may be. And if you happen to match that natural frequency, what happens to the vibration of the bridge? It grows and grows and grows. Now, it's still pretty unlikely that the bridge would fail, but possible, conceivable, yeah. All right, I want to go back to the definition of simple harmonic motion for a second. We said it was the motion in which the restoring force was proportional to the displacement. In other words, F was equal to negative kx, x being the displacement in meters, and k being the spring constant or the elastic constant in newtons per meter. Of course, F being the restoring force. Now, I'm going to put an equation in brackets here. F is equal to negative kx, but F can also be equal to positive kx. What force would this be? If that's the restoring force, what force would this one be? The restoring force is that force that pulls it back to its natural position, and that's a negative kx. The positive kx would simply be the applied force, how hard you pull on something to stretch it a certain amount. All right? Now, we've talked about this a little bit before, but we've never actually used it to solve mathematical problems. That's what we're going to do today, is use this whole definition of simple harmonic motion, which really boils down to this law that we call Hooke's law, to solve some problems. And we're going to move from there on to elastic potential energy, which again, we talked about a little bit back in Unit 2, but we didn't actually use to solve any problems. All right, 7.3 and page something. I don't have the page number written down there. Page 354. Thank you, Bruce. A spring has a spring constant of 30 newtons per meter. The spring is pulled to a distance of 1.5 meters from the equilibrium position. What's the restoring force? Well, what do we got here? We got K is equal to 30 newtons per meter, and we got X is equal to 1.5 meters. This should be pretty easy, I think. F is equal to negative Kx. Now, again, technically the applied force is positive Kx. If you were asked to solve for how hard you had to pull in order to get it that stretch that much, then you would use positive Kx. But you know what? I'm not going to lose any sleep over the negative and the positive in that case. If you solve for F using Kx or negative Kx, I'll give you marks for that. Technically, though, this should be negative Kx. Yep. Yeah, I wouldn't take any marks off for that. No. So we've got negative 30 times X is 1.50 meters. We do the math there, and it's a nice, easy one, negative 45.0 newtons. So the negative 45 doesn't mean 45 to the left here. It just means 45 back to where it started from, right? Positive technically means away from where it started from. What if I had a spring that was vertical like this and a mass on the end of the spring? and I said, what's the value of X? How would you do that? Well, you'd say F is equal to KX, right? Or negative KX. In this case, it would actually be KX because the only thing we can find here is the applied force. What would be the applied force on this? Whatever the scale reads? Okay, if it's a spring scale and it has a reading, sure. But let's say it's just a spring with a mass on the end of the spring. We know that X is what we're looking for. K would be 30 newtons per meter if it was this still the same spring. F would be, what is it? Yeah, what's A? 9.81, m times g, right? M times 9.81. Because the applied force, the force that's pulling it down, would be gravitational force, right? All right, let's have a look at a couple questions at your desks for a few minutes here. On page 354. Let's have a look at number 2. It says a spring requires a force of 100 newtons to compress at a displacement of 4 centimeters. What's its spring constant? First of all, I catch the fact that it's centimeters, not meters, and I want to convert that. Circle in red to remind ourselves of that. Want to find the value of K. I'm going to use an equation F is equal to K times X this time, as opposed to negative K times X. And why should I do that? Why negative? Why not negative KX? Yep. Yeah, we're talking about the applied force here. This is how much force is required to compress it, not much how much force it's pulling back to its equilibrium position with. So we're going to say K is equal to, K is equal to F over X. My applied force is 100 newtons, and my displacement is 0.04 meters. Do the math there, works out to be, I think it's 2,500 newtons per meter, but we should round that to 2 significant digits. So we'll make it 2.5 times 10 to the 3 newtons per meter. Good? Not crazy hard, eh? Okay, let's take a look at another one. Page 357. The spring is hung from a hook on a ceiling and a mass of 510 grams is attached to the spring. The spring stretches at a distance of 0.5 meters. What's the spring constant? Looks familiar. I think we've done something like this, right? The spring is hung from a ceiling. There's a 510 gram mass. We want to convert that to kilograms. Stretches at a distance of 0.5 meters. What do we got here? Well, we know that F is equal to, is it KX or negative KX? Do we have an applied force here or a force that's pulling it back to its equilibrium position? It's an applied force, right? What supplies the applied force? What's causing the applied force? It's the mass and gravity, right? So we're going to say the force is also equal to m times g. So mg is equal to k times x. We're dealing with the magnitude of gravity here. Technically, gravity is downward, but we want the magnitude to be equal to the Hooke's law force. So we're just going to make it a positive value of g. 0.510 kilograms times 9.81 equals k times the value of x, 0.500 meters. Let's say 0.51 times 9.81 divided by 0.5 equals 10.0062. We're going to round that to 3 digits, so K would be equal to 10.0 newtons per meter. The value of K should always be a positive value. If you've made a mistake with your equation, right, Kx versus negative Kx or something like that, I can live with that. Okay, that's not the end of the world, but let's at least recognize that when we get the value of K, if you happen to get a negative value of K, let's recognize at least that that should be a positive value. Okay, so just drop the negative in that case if you happen to get a negative value. Let's do these questions, please, on page 357. Let's do number 1 right now. 5 people with a combined mass of 275 get into a car. The fact that it's 5 people is irrelevant. What's important is that we have a mass of 275 kilograms. And that mass of 275 kilograms in this car pushes downwards on the car. In fact, compresses all 4 springs a distance of 5 centimeters. Now, what I would do What I would do in this case, because we have 4 springs compressed 5 centimeters, I would say my compression is 0.20 meters. 5 centimeters times 4 springs, a total compression of 20 centimeters. That's my preference. We want to find the spring constant of the springs here. All we're going to do is say F is equal to K times X. It is an applied force here after all. M times G is equal to KX. We're going to say K is equal to mg over X. So we're going to say it's 275 times 9.81 divided by 0.20. And what do we get there? I think it was 13,000 or something like that. 488. And that would be newtons per meter. But we got to convert that to 3 digits. Yeah, 1.35 times 10 to the 4 newtons per meter. Good. Now, the other way to tackle this is to say the displacement is 5 centimeters. But if you make the displacement 5 centimeters, then what do you got to make sure you do? If you're analyzing each spring individually, what do you got to do? Divide 275 by 4. Not by 5, but by 4. And if you do that, what do you get for the mass there if you divide that by 4? 68.75. So we'd say here, K is equal to mg over X. We'd say 68.75 times 9.81 divided by 0.050. And lo and behold, we get 1.35 times 10 to the 4. So either way gives you the spring constant of each spring. Okay? How many people are still working on number 2? Okay, we'll give you another... we'll give you 1 more minute for question number 2, and then we'll take a look at it. All right, we're going to do that now just so we have time to finish it before the weekend here. It says 2 springs are hooked together and 1 is attached to a ceiling. Spring A, let's draw this out here, okay? Here's the ceiling. Spring A has a spring constant of 25 newtons per meter. So we'll call this one spring A. K is 25 newtons per meter. B has a spring constant of 60 newtons per meter. There's a mass of 40 newtons attached to the end of it. Oh, wait a second. It says a mass weighing 40 newtons. That's not the mass, is it? What is that? What's that number that's given to us there? 40 newtons. That is mg already. That's the weight of the force of gravity. Yeah, they give us a bit of a break here. Instead of having to multiply m times g to get the applied force, they give me the value of m times g already. Somebody was asking me earlier, if we take the weight and we divide it by 9.81, do we get the mass? Yes. But then what would you have to do with that? Multiply it by 9.81 to get the weight. So you divide it by 9.81 and then multiply by 9.81. Guess what you get when you do that? 40 newtons. All right, what's the total displacement of the masses? The total displacement of the masses. Well, what you're going to have to do here is analyze them separately this time because the spring constant is different for each one. We're going to say for the first one, X is equal to F over K. The force applied is what? 40 newtons. We're applying 40 newtons to both of them, right? So 40 newtons divided by 25 gives me a displacement of, is that 1.6 meters? And then we're going to say for the green one here, X is equal to F over K. F would be still 40 newtons divided by K, which is 60 newtons per meter. That's going to give me 0.6667 meters. And then what are we going to do when we have to find the combined displacement? We're going to add them together, right? 1.6 meters plus 0.6667 meters equals 2.23, 2.3, 2.26, or rounded to 2 digits, 2.3 meters. Now they've got a negative there, but it doesn't matter. Doesn't matter there. We're talking about displacement, not like left, right, up, down. We're talking about displacement, stretching, compressing. Don't worry about that. Yep.